Let's suppose that we have a TCP sender that's sending packets where the sending rate is controlled by the window W and it's receiving X. Now at any time, if the window is W, only W unacknowledged packets may be outstanding. So the sender's sending rate, R, is simply the TCP window W divided by the round trip time of the path. So the rate is W over RTT. Now remember that TCP uses additive increase, multiplicative decrease, or AIMD congestion control. So for every W AX received, we send W plus 1 packets. And our TCP sawtooth will look something like this. We'll start at a rate W max over 2, increase the window to W max, and then when we see a drop, we will apply multiplicative decrease and reduce the sender's sending rate to W max over 2 again. So here, right at the point of a packet drop, this represents the maximum number of packets that can be in flight. So again, the required buffer is the maximum number of packets that can be in flight, or simply the height of this TCP sawtooth. Now we know the rate is W over RTT, and we'd like the sender to send at a common rate, R. And if we'd like the sender to be sending at the same rate before and after it experiences a loss, then we know that the rate before the drop must equal the rate after the drop. So then we can set these two rates equal. We know that the RTT is part transmission delay, T, and part queuing delay, which is the maximum buffer size of the bottleneck link divided by the capacity of the bottleneck link. We also know that after reducing the window, the queuing delay is 0. So we can replace the term on the left with W old over 2T plus B over C, and we can replace the term on the right with W old over 2, because the congestion window has been reduced by half, divided by 2T, simply the propagation delay with no queuing delay. Now, if we solve this equation, we find that the required buffering is simply 2T times C. Now, the rule of thumb makes sense for a single flow, but a router in a typical backbone network has more than 20,000 flows. And it turns out that this rule of thumb only really holds if all of those 20,000 flows are perfectly synchronized. If the flows are desynchronized, then it turns out that this router can get away with much less buffering.